Hello and welcome back. Let's continue with our lecture on general theory of relativity. Earlier lecture we have seen the connection between the Lagrangian and non-inertial transformation. How Lagrangian formalism helps you to handle non-inertial frame in comparison to Newton's equation of motion. Eventually we get the same equation of motion. Let's make a more geometric connection. In this lecture we'll be dealing some of the aspects of the geometry, that is we are also defining the covariant and contravariant vector fields and how does it naturally comes from the Lagrangian equation of motion. Let's continue with that. Before we continue with the lecture, let's have a quick quiz on physics which we are dealing with, that is inertial frame. Let us look at what is called the shootout at inertial frame. Here is a very puzzle. Answer is very trivial and simple. However, let's go ahead with this. We have two twins, identical twins, whose name is Sita and Gita. Both dislike each other and often have a fighting with each other. So their father decided to pack them off or separate them. You put one on an inertial frame which is moving at v, or we can say that as a reference, and another one in the frame which is moving with respect to the first one. That is called the Sita is a reference and the Gita is moving with the velocity v. Now let's say that this is a uniform velocity v and both of them carry an identical revolver and then shoot at exactly same time, as they are identical twins born at the same time. Now one is moving and shootout happens, and question is who get hit by the bullet first. So this is simple exercise on the addition of velocity of particle. So you can solve this simple problem and give your answer. Answer is either Sita or Gita or O1 or O2. Idea is very simple. Velocity get added when you do an inertial transformation. But this one need to figure out which bullet reaches the target first. First, we are going to measure distance along the curve. So we have a particle moving, or rather following a Newton's laws of motion through Lagrangian system. So the transformation could be inertial or non-inertial. We don't really care. If it is the inertial, we know it is quite simple. Otherwise, we have a Lagrangian system. So we want to measure how much distance particle travels along its path in a small time interval dt. In an inertial coordinate system, the relation is basically written as a dxi by dt is equal to v, and the equation of motion dv by dt is equal to 1 by m into fi. This is basically equation of motion. On the other hand, if it is not inertial frame, then you know the equation of motion can be obtained from the Lagrangian equation of motion. The basic identity which we are going to use is a tangent vector, that is dx by dt is equal to v, and measure the displacement. The displacement for a small time interval can be written as dxi is equal to vi into dt. So this is displacement vector from a position xi for a small interval dt. So if you want to calculate the displacement, that is the distance it traveled, then we got to find magnitude. The length of the displacement vector is given by dl square is equal to dxi into dxi, which we can write as v dot v into dt square. In the inertial frame, we know that the vi is a twice Lagrangian, or dl square is given as a twice the Lagrangian into dt square. Can write it as delta ij dxi dxj. So delta ij here is what we call is a Kronecker delta. So you know that there is a delta function which is a Dirac delta function, which is the most popular delta in the physics, which is an improper function. However, here we are not talking about Dirac delta function. What we have is a delta ij. I have used one up, one down. Now onwards, we will be distinguishing between the upper and lower indices. So far we have not distinguished, so you could write as a both upper or lower. It doesn't matter. In this case, we distinguish them as a delta ij as upper and lower. Now it is equal to 0 if I is not equal to j, and it is equal to 1 if I is equal to j. This is basically an identity matrix in n dimension. You can choose any dimension. In 3 dimension, it is an identity matrix. Let's quickly look at some of the trivial properties of a Kronecker delta or delta ij. So first property which we have trivializes the matrix multiplication or multiplication with the tensor or vector indices. For example, if you have ai delta ij, so here summation over the repeated index I, one should come as a upper and other as a lower, then what you would get is a aj. So this is simply the property of identity matrix. If you multiply by an identity matrix, you are going to get the same matrix. That is what is shown by this equation. But whenever you have a repeated index over a delta ij, it is simply not going to do anything. You got to change the index from I to j. Now the next property is the same thing with the lower indices. I have explicitly written so that you will not get confused. Aj delta ji. Here summation is over j, and then you would get the same vector ai. So there is a difference between the upper and lower indices. That's what we are going to see soon. Now here let's simply look at this as a property of delta. When summed over, it is going to get the component or same thing as a multiplying by identity matrix. The next property is the summation of Kronecker delta itself, that is delta II. So summed over the repeated index I, which is basically trace of identity matrix, which gives the dimension of the matrix itself. You do this in 3 dimension, you would get the value of 3, and corresponding to every dimension, you would get a delta II as a dimension of space which you are using. So this delta ij basically simplifies the calculation. We have seen that Dirac delta function and integrated it simplifies. Same way here summed over simplifies a lot. It is important, useful second rank tensor. So let us say that what we are doing here is basically using a delta ij to write the kinetic energy or displacement along the path traveled by particle in a small interval dt. So in any coordinate system, we can simply write down this as a Lagrangian, twice the Lagrangian into dt squared. So what basically we obtained the expression for Lagrangian when transformed to an arbitrary coordinate system from an inertial coordinate system. We have gij xi dot I xi dot j into dt squared. So that is what we have. So after expressing dt or removing dt and cancelling it out, what we get is a distance traveled gij into d xi I into d xi j. So this is basically an identity which shows that kinetic energy multiplied by dt square or the coefficients of kinetic energy in the curvilinear coordinate basically represents the distance between the 2 points in the coordinate system. So this is what we call is a metric in that space which suits to the adapted to the curvilinear coordinate system. So the coefficients of kinetic energy or free particle Lagrangian may be considered as a measure of distance or the metric on a curvilinear coordinate. So this is what we are trying to show. It is not just the distance along the particle trajectory, it is in fact represent the distance in the coordinate system itself. Let's look at a quick example. Let's take a transformation to a plane polar coordinate and compute the metric. The transformation from Cartesian to polar coordinate system and reverse is given by 2 set of equations, that is x is equal to r cos theta and y is equal to r sin theta. On the other hand, inverse transformation given by r square is equal to x square plus y square tan phi is equal to y by x. So once we have this, we have to basically compute the kinetic energy to get the coefficients of kinetic energy or the metric tensor. dx is given as a r dot cos phi minus r sin phi dot. Same way, y dot can be computed easily. Y dot is equal to r dot sin phi plus r cos phi dot. Now once we have this, we know that the Lagrangian is given by x dot square plus y dot square in the inertial frame, and the same thing we can substitute this x dot and y dot and compute the Lagrange in the polar coordinate system. We can square it, we get the three terms, that is x dot square is r dot square plus cos square phi r square sin square phi dot, and then minus 2 r cos phi sin phi r dot phi dot. Same way, y dot square can be written as r dot square sin square phi r square cos square phi dot square plus 2r cos phi sin phi r dot phi dot. So this cross term getting cancels because they come with the negative signs, and they too get cancels out, and you left with a much simpler expression, that is Lagrangian now can be written as a r square phi dot square. So this represents the distance element in the plane polar coordinate is given by dl square is equal to dr square r square d phi square. This displacement between the point r phi and r plus dr phi plus d phi. Now from this we can simply write down the metric. It is a 2 into 2 matrix, that is Gij is equal to 1 0 0 r square. So in this case resulting metric is also a diagonal metric. So most of the time we are looking at the orthonormal coordinate system. Sometime you can also have a non-orthonormal coordinate system. We will come back to that little later. Now this is a metric in the plane polar coordinate. So you can do this exercise to various other coordinate system. We are going to see an homework problem. Here is a homework problem. Let's look at another example. Here we transform a 3D space to 2D space with a constraint. Earlier, I have said that the transformation need to be one-to-one. That means you cannot have a projection or dimensionality change. However, here we can do this by an interesting trick which you might be also familiar with, Lagrangian system, that is called the constraint. You can have holonomic constraint that is given by a specific equation, and the dimension or effective degree of freedom of Lagrangian reduces. So this way, we start with the three-dimensional space and give a constraint that one holonomic constraint would reduce the degree of freedom by 1. So this way, we can transform three-dimensional space to two-dimensional space or a surface. So example here is that we have a Lagrangian in 3 dimension, that is L is equal to m by 2 x dot square y dot square plus z dot square, and the constraint is that the motion is always such that x square plus y square plus z square is always equal to r square, where r square is constant. You might be already familiar with it, what happens here. So all you have to do is the transform from a Cartesian coordinate system to polar coordinate system with this constraint and get the effective Lagrangian of a system in 2 dimensions. Theta and phi, our degree of freedom remains, and then once you get Lagrangian, which also represents metric in the new coordinate system, you have 1 week to solve this problem and upload it on VLearn. Please do the details. So this is how we are treating surfaces and reduction of dimensionality using the constraint both in Lagrangian as well as any geometry. Let's go back to curves again. Here, let's do something more interesting. Let us start from a coordinate system O1, that is x given as a xi is a coordinate system. Let's not worry too much about inertial nature or non-inertial nature of the transformation. We know how to handle them using the Lagrangian or kinetic energy and so on. So we generally have a curve. Curve is parameterized by real parameter. We call it a lambda. And the curve is a mapping from real line space Rn, and we write or denote it as a xi of lambda, which represents the curve. Now we know that the tangent vector for this curve with respect to parameter lambda is given as a ti is equal to dxi by d lambda. So this is a tangent vector. So we have a curve which is the coordinate xi parameterized by lambda, and then we have a tangent vector which is dxi by d lambda. Now our main interest is how does tangent vector vector behaves under the coordinate transformation. That is, we do a coordinate transformation from xi to x prime I. The x prime I is a new coordinate system. Both need not be inertial coordinate system. Once we say that there is coordinate transformation possible, then we do have a bijective mapping, that is from xi to xi prime and x prime I to xi. So that is what relation we exploit to represent our curve, and then find the tangent vector and how this tangent vector looks in the both coordinate system if there is any relation between two of these. So here we get the idea of what is called the Contra-Variant vector. Let us examine how the component of tangent vector transforms under the coordinate. So let's start with the new coordinate system. What we have is a t prime I, that is a tangent vector in a x prime coordinate system. There it is given as a dx prime I by d lambda. That is a definition of tangent vector. Now we know the transformation rule for going from x prime to x or x to x prime. We use a chain rule while differentiating, that is when we do dx prime by d lambda, because x prime are now dependent on x, we can use the chain rule, that is dx prime I by dxj by d lambda. So this is using the chain rule. Now summation is assumed here over the repeated index. You can see that this is done for all the coordinate and multiplied by dxi by d lambda. We can rewrite this as a t prime I is equal to dx prime I by dxj into tj, where tj is a tangent vector to the curve in the x coordinate system, which is simply dxj by d lambda. So using that the definition, now we have a relation between the tangent vector between the two coordinate system with a transformation rule. Now we can use this transformation rule to tangent vector. In addition to that, we find that the many of the vectors which behaves like a tangent vector to a curve are transforming using the same rule. All such vectors which transform with this rule under the coordinate transformations are called the contravariant vector or the tangent-like vector. They are usually denoted by upper index. That means t prime I, that is upper index. That means contravariant vector is defined as a property how it transform under coordinate system, that is dx prime I by dxj into tj. So this is how a contravariant vector transforms. So we find that there are the whole set of vectors in a given Rn which simply can be mapped as a tangent to a curve. So, and all of them transform like a covariant vector. Is that all the time? Why do we specify this with a specific name as a contravariant vector? Are there any other type of vectors? Closer look at the another type of vector which are called covariant vector. In physics, while formulating, in addition to tangent vector, often we also come up with the another type of vector. The tangent vector means velocity like vector. Now another vector is basically given as a normal to a function or gradient to a function which is orthogonal to the phi of xi is equal to constant hypersurface. So if you have a function phi of x in your space of n dimension, then you can have a gradient or normal vector which is defined as d phi by dxi and I is equal to d phi by dx. This vector is called the normal vector, and they are called normal because they are orthogonal to the phi of x I is equal to constant hypersurface. Now let's see under coordinate transformation going from xi to xi prime, how does this normal vector transform? We start as the same way. We start with the x prime coordinate system. We have a function phi defined there, and then define the gradient n prime of I is equal to d phi by dx prime I. Now we make a coordinate transformation as we have done earlier, because x prime I can be written in terms of xi, and again we use the chain rule, that is n prime I is equal to d phi by dx prime I. That can be written as d phi by dxj into dxj by dx prime I. So this is basically chain rule. Further, we can write this as a normal vector in the x coordinate system, which is given by nj, and then this is a transformation which comes in, which looks quite different than the contravariant vector. We rewrite them in the proper order, and then we have n prime of I is equal to dxj by dx prime I into nj. So the summation over j here and I is a free indices. This is a way a normal vector to a function or the gradient of a function transform under the coordinate system, and that kind of a transformation or the vector which transform like this are called the covariant. These are all orthogonal to the hypersurface. Phi of xi is equal to constant, and in general any vector which transforms using this transformation rule, which we call, is a covariant vector, which are usually denoted by the lower indices. Now we have a two type of vector, one which is called the contravariant vector, which are analogous to the velocity or the tangent vector to the curve, which are represented by the upper indices. We have another type of vector which are called the covariant vector, which are similar to gradient of a function, or which they are called the covariant vector, which are represented by the lower indices. So this is the two type of vector. In addition to function, simply called the scalar, remain same in all coordinate system. This brings in the relation between the covariant and contravariant vector and to the norm. In a curvilinear coordinate system, the repeated index over one covariant and one contravariant index represents the summation. Now that we are able to distinguish between the upper and lower indices, that is, the upper indices is contravariant and the lower indices is a covariant, the Einstein summation convention is valid only when the repeated index come over one as a contravariant and one as a covariant. So otherwise, if both are contravariant or both are covariant indices, even if they are repeated, they do not mean the summation. Now let's look at this product, t prime I, n prime I. Let's see how when the summation is done over this, how does it transform. Now we use the transformation rule. The t is a contravariant vector, so we use a contravariant transformation rule for that. That is x prime I xj into ti. Now we have a n as covariant vector. For that we use a covariant transformation rule, that is a xk divided by del x prime I and nk, so summed over k. So now we can rearrange the term. We can write this partial differential or transformation matrix to one side, and then we see that this is summed over, and then we know what happens here. This is simply using the chain rule. We can write it as a dxk by dxj into tj into nk. Now this is a delta kj, the delta kj, because this is an identity matrix. When you partial differentiate the coordinate system with itself, you simply get an identity matrix because they are not dependent on each other, and that is why you are getting a delta kj, and then that is summed over. And now we know how to use the property of delta kj, and then we have tk and nk summed over with the one covariant and contravariant. That means that it does not transform, it just transforms as a scalar. Dot product, which is called the contraction, leads to the scalar. We may define the dot product between the two vectors contravariant and covariant, that is t and n, by simply doing the product, and that is what we call is the length of the vector, or L square is simply defined as a Li upper into Li lower. So this defines basically a dot product. Now one of the advantage here, the dot product allows you to have a relation between the lower and upper indices, that is covariant and contravariant, because dot product of, or the length of the vector, is basically product between the upper and lower indices, and that can be exploited to figure out the relation between the upper and lower indices. Now once we have seen the dot product, we may also see the higher rank tensor. We hear higher rank tensor can be simply obtained by multiplying or taking the outer product of the vector. It means you simply multiply them without summation. That means with the different indices. Suppose I have a vector Ti, then I have a Ti Tj basically represents the tensor of second rank. So how we can make this out? We can make this out using the transformation rule. Now we transform xi to x prime I and see what do they behave. Ti is contravariant, n is a contravariant. So we use the contravariant transformation rule for both these, and then we have this product, and we can suitably rearrange, and you see that this basically is a transformation for the second order contravariant vector. So we can have in general, without having to multiply same vector, we could have sometime the quantity which transform with the two order, that for example a prime ij is equal to x dx prime j dx prime I by dxk into dx prime j by dxl a kl. So this you can see this transform like a second rank contravariant. We can also have a second order covariant as it have a two covariant transformations multiplied to them, or we can have mixed one contravariant, one covariant, n contravariant, n covariant, simply based on the how many times you are using contravariant transformation and covariant transformation to get to new coordinate system. So you can have any higher order tensor. Mathematically it can be simply written like this. What does physically it tells, we will come back to that later when we talk about the various physics, probably when we talk about tidal force and things like that. Now let us continue with how we can define a metric tensor. We have already said that the Lagrangian, when we transform kinetic energy, it also represents the distance between the 2 points for given a small displacement dxi. Now you already see that dxi dxj is a second rank contravariant tensor, and when we have take the dot product with the gij dxi dxj represents the distance or the scalar. That means the tensor gij should be a second rank covariant tensor. A metric tensor is a second rank tensor which represents the distance between the 2 points, or we can also have one which represents the distance, where distance dx square can be written as gij dxi dxj. The metric tensor is also symmetric. That symmetric means we can write gij is the same as a gji. So when you flip the indices, there is no difference. When the tensor is symmetric, then when you flip the indices, there is not going to be any change. If they are not symmetric, then gij is not equal to gji. But metric tensor is always a symmetric, because we can see that it defines the scalar with the dxi dxj, which is the outer product of dx dx, which is going to be symmetric. It doesn't matter from which side you write dx. dxij is always going to be djx. So this way we have made a transition from Lagrangian system to tensors, where we have defined covariant tensors and contravariant tensors. So one of the important questions here which you might want to think about is again connection with the Lagrangian mechanics. What we have is a Lagrangian which acts like a distance or the dot product, and we know how to define the metric which is given as a half gij dxi dxj, and that is what is given. Let us look at what we call is a generalized moment. Generalized momentum pk is given as a derivative of Lagrangian with respect to dx dot k. So now this quantity is a covariant vector or contravariant vector. So let us look at this. How does it transform? So let us do dxl by dl by dx dot k is equal to half d by dx dot k into gij into x dot I x dot j. So now we can differentiate it. In general, during the transformation, we have seen that the gij's do not explicitly depend on the velocity. We have factorized all the terms which depend on the velocity to write it as a quadratic term like here. So gij do not depend on the position. So this makes makes it Gij doesn't depend on the velocity. That means that we can simply take it as a constant because it's a partial differentiation. So bring in the differentiation, we have a two term because of the product relation, and then they are all same. We can use the property of delta Ij because it is a differentiation of the velocity with respect to velocity, which leads to delta Ij because you differentiate same component with same, you get 1. If it is a different component, then you would get 0. And then you have two terms which are same, and then you get a Gkj x dot j. So pk is equal to this. So that is like a lowering the index. You can see that we have already seen the metric is a covariant tensor of second rank, and this is a contravariant vector of first rank. And then we are summing up. Summation means that cancels out, which leaves out that we have a one covariant vector. So the momentum is actually a covariant vector because it is defined in this way. So the generalized velocity is a contravariant vector and generalized momentum is a covariant vector. But the relation is established to the metric. So metric convert all the contravariant component to covariant by taking the dot product. So this is one of the way to reduce the upper index to lower index or contravariant vector to covariant. So we will get to more properties of a metric and how do we convert contravariant vector to covariant vector in the coming lecture. Let me stop here. It has already become heavy on the tensors, and we will soon look into a couple of more properties and then get back to physics. Let me stop here and continue in the next lecture.